A very good evening to all the learners. Let's wait for 2 more minutes. Let a few more learners to join and then we will start with the session. Okay, let's start everyone. First of all, a very good evening to all the learners and a warm welcome to this session. In this session, we are gonna do revision of the important concepts of Machine Learning 1 module. My name is Dr. Reena Duggal and I'm gonna take you through this session, okay? So let's do a quick audio and video check, everyone. Please say yes in the chat window if you are able to hear me and see my screen. Let me do this test also. I'm changing the slides. People, please confirm that you are able to see the different slides. Please confirm that. Okay. No, slide did not change. Okay, so I think there is some issue with this thing, okay? So don't worry, people. It is not in slideshow mode. Okay, let me try this. Okay. How about this, people? I'm changing the slides. Can you please confirm that you are changing the different slides? I was having this issue in the session before also. Okay, great. Now it's working. Great. Okay. So again, a few rules before we start. This session is getting recorded and the recording as well as all the resources that I'm going to use in this session will be shared with you shortly. This is a 3-hour session. We're going to take a break of exactly 5 minutes at 8:30. We have a lot of ground to cover. So I want you to be focused, attentive, interactive in the class. I'm going to ask a lot of questions, give you tips and tricks. give you a few sample questions also, which you can expect the similar ones in the exam. So please pay attention and ask as many questions as you want about those concepts. Okay. And again, the full benefit of this session can be taken only if you have already gone through the async material or the pre-recorded videos of these concepts. Okay, so with that context, let's start. Okay, so we're going to cover linear regression, logistic, clustering, and Python coding questions. I'm going to spend most of my time in explaining linear regression concepts because there are a few in this. Then I will talk about logistic regression and probably spend some time on clustering. And finally, we're going to end with Python coding questions. Now, you will not get any Python questions related to machine learning because, uploading a data set, reading a data set, and then do some processing on it. It's a little difficult with the current Python console. So here our objective is to test you on intermediate Python skills. Okay, so you must have attempted some of the probably beginner questions on Python in your initial exam. So in this exam, we're going to test you on intermediate Python coding, and I'm going to give you a couple of sample questions which will give you an idea what type of questions you can expect. Okay, so without further delay, Rini, yes, Python question. I don't know what is your last data toolkit question, but I just want to tell you that these will be intermediate Python question, and I'll give you examples. Okay, great. So as you all know, machine learning techniques are divided into two types, unsupervised and supervised, and everybody should be crystal clear about these different techniques. Whenever we have a target variable given, that what we want to predict, then we are using supervised learning. When we do not know what we want to predict, we just have some bunch of data which we want to put in groups in such a way that the items in one group are very much related to each other and items in different groups are very different from each other. Then we are in the area of unsupervised learning. Okay, and clustering is one technique where we create clusters or groups of similar data. Okay, under supervised learning, we have been given the target variable, which helps us to differentiate between good versus bad. And here we deal with two types of algorithms, is classification and regression. Whenever the target variable is categorical in nature, then we use classification techniques, classification algorithms, okay, when the target variable is categorical in nature. Okay, when the target variable is numerical, okay, it's numeric in nature, then we use, or continuous in nature, then we use regression algorithms. There are various algorithms under these categories also. We're going to just concentrate on linear regression for regression and logistic regression for classification purpose. Okay, and let's start with linear regression. It is a supervised regression model, as you all know. The target variable, or it's a labeled data. It allows you to make predictions from labeled data if the target variable is continuous. We look for two factors in linear regression. The first factor is which variables are the most significant predictors or most important predictors for the outcome variable. And also we look for how accurately we can predict using these predictors the value of our target variable. Okay, so we want to find out how significant our regression line is. Okay, so these are the two things that we're looking to solve using linear regression. Okay, now let's start with the very basics. So let's take this example of simple linear regression where we have one predictor. So using marketing budget, we want to predict how much sales will be there. So if I plot a scatter diagram like this, we want to create a model. What is a model here? Model is a line here. Okay, so we want to create this line which will best fit this data. Now, as you can see, there can be number of lines that you can create using this, using this data. Now, which line is the best fit line? How do we figure that out? So every line, as you know, in geometry has a equation attached to it. And as you know, so here it will be sales is equal to beta naught plus beta 1 times marketing budget. So for this line, probably the equation can be sales is equal to beta naught dash plus beta 1 dash into marketing budget. And let's say for this line 3, it can be sales is equal to beta naught double dash beta 1 double dash marketing budget, where beta naught, beta 1s are our regression coefficients, which will give us the model. Now, out of all the possible combination of beta naught and beta 1, we will go with that combination which will give us the minimum error. Okay, which will give us the minimum error. Now, what is this error thing? So error can be figured out using this graph. So let's look at this. So this is my prediction line. Let's say this is one of the line from my previous slide. Okay, we call it y hat. It means this is the predicted line. This is my actual value. My predicted line has predicted this value for this 200 thing. So I made this mistake. This is my error. Similarly, I made this mistake, I made this mistake. So these all the errors that I have made. So how can I, so if this is my marketing budget, this is my actual sales, which is coming from the past data. If I'm looking at it, this is my predicted sales. So using this line, I have predicted my sales. And as you can see, there is some difference between actual sales and predicted sales, and this is called my error. So for one point, we have data, this is error 1. Another point, another data, E2, where E2, E1 is actual minus predicted. Similarly, so on, we can find errors for all the different points. So in order to minimize error, we need to minimize this error. So what we want to do, we can do sum of all these errors and then try to minimize it. But the problem with summing it as such is that some errors can be negative, some can be positive. So we cannot just simply add them. So how to get rid of the signs? We can do two options. We can do square of them, we can do absolute of them. We have seen that when we do square of things and try to run many iterations to find out the best values of beta naught and beta 1, the square method gives better speed and better efficiency. The algorithm converge faster when we are using square in comparison to absolute. So that's why the square method is the most popular one. So what do? We do square of all the errors. Okay, and this will become my total error. And I try to convert it to a mathematical equation also, something like this. Now you can fit in EI is YI, which is my actual, minus Y hat, which is the predicted. Okay, and this you know that y hat is equal to beta naught plus beta 1 x. So I put that value here. It will become yi minus beta naught plus beta 1 x whole square, and this will become my total error, and I also call it residual sum of square or RSS. And this becomes my cost function. So those values of beta naught and beta 1, which will give me the minimum cost function, which will be my ideal values of beta naught and beta 1. And how do we find those? I use an optimization algorithm called gradient descent. In that, the system runs many times, many iterations with different values of beta naught and beta 1, and then try to find the best fit line using cost function. That's why this method is also called OLS method, ordinary least square method. Okay, so that's how we get the ideal values of beta naught and beta 1, and that will be our best fit line, which will give us the minimum error terms. Okay, this was only for one predictor. You can extend the same idea with beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus so on. When we are dealing with multiple linear regression using multiple predictors, the concept will remain the same. Okay, so this is the basics behind linear regression. Okay, now let's dig deep and let's look at other things related to linear regression. Okay, now if you know, there are two ways we can create a prediction model using linear regression in Python. We can use stats model library or we can use sklearn. Stats model give us more measurements and give us more information about what is going on inside the model. Okay, so for this example, I have run the stats model library, use the stats model library. I have used house price data and it has given me this output. Okay, now there are so many things there. I will only talk about which are the important ones. And the very first one here is called R squared. No, Sai, the mathematics behind gradient descent will not be asked. Okay, you just need to remember it is an optimization algorithm which runs many iterations and try to converge, means come to that those values of beta naught and beta 1, which will give you the minimum cost function. Okay, so when I run stats model, this model gave me R squared as 68%. What does it mean? So you can assume you can relate R squared to be like an accuracy of the model. Okay, now how it is calculated, let's dig deep into that. So again, I'm showing you a scatter diagram. Okay, now how do we find R squared? We find R squared, you can see that this means that how much R model better than base model. So we need something to compare our model, that how much better it is from a model. So we take a base model, which is the minimum basic model that somebody can create. And what is this base model? Let's assume we do not have given any predictors. We only have target variable. And somebody asks us to do prediction. Let's say house price is my target variable. I have only given one column. There was a home that was sold at 10,000, another home that, let's say, 8,000, another home, let's say 12,000. And somebody asked me, so if there is a new house on the market, based upon this data, can you predict how much that will be cost? So I don't have anything else. So the bare minimum thing I can do it, I can find out the average sales of previous home prices. It comes as here in this scenario as 10,000. And I can make a prediction that the next home will be of, this home is of $10,000 price. So this is my very basic prediction. So I take my base model as Y bar, and anything I create, I will compare it with the base model to check how accurately I am predicting. Okay, so once so this is my base model here. Then I create my model, and now I'll check how much good I'm doing in comparison to base model. How will I do that? Again, I will take this point. Then for this point, how much my base model is predicting? This much. How much I am predicting, my model is predicting? This much. So this is, you can consider my total deviation for this point from the base model. Ideally, I should have predicted this whole deviation. I should have explained this whole deviation, but my model is not perfect. It was able to explain this much deviation. Okay, but it was not able to explain this deviation. So this is the error that I have made. So this is my explained variation, which I was able to predict successfully for this data point, and this is the error that I made. This is same as residual that we talked about in the previous slide. So I want my green area to be bigger and my red area to be smaller in order to make a good model. Okay, so R square, so I calculate, so for all the data points, I add this explained variation, explained deviation. So my R square will come as explained variation, sum of all the explained variation, divide by the total variation or deviation. One and the same thing. Or in other sense, I can say it 1 minus unexplained variation, or the error that I made, divide by total variation, which will become as 1 minus RSS divided by TSS. TSS is total sum of squares. RSS is residual sum of square. Okay. Now, the more deviation I am able to explain, the better will be my R square. So better will be my model. So I am targeting a large R square. So if the value of R square varies between 0 and 1. Okay, so I am targeting my R square to be closer to 1. I'm trying to make my model that is able to explain the deviation 100%. Okay, that is the idea behind R square. Okay, so R square is also called the coefficient of determination. It is a key output of regression analysis. It is interpreted as the proportion of the variance in the dependent variable that is predictable from the independent variable. So here I can say that if my R square is 68%, 68% of variation in the house price, I am able to predict using different predictors. Okay, so R square helps to determine the predictive power of a regression model. It ranges between 0 to 1, and this is the formula behind it. 1 minus RSS divided by TSS. I can also show it in form of mathematical formula. So I can also say it, what is my RSS, what is my error, this is my actual, this is my predicted, this is my base model. So RSS is actual minus predicted. So I can also say it like this. And what is TSS? Actual minus base model. Or I can say it ESS, which is the explained variation divided by total variation. What is explained? Explained is predicted minus base model square divided by total sum of square. So this is the mathematical formula behind R square. Once you understand it, it's not a difficult thing to grasp. Okay, so the more variation I'm able to explain of the dependent variable, the higher will be my R squared and better will be my model. It is a general guideline that any model having R squared closer to 80% is considered a good model. Okay, so here we have given the mathematic formulas behind these variations. Okay, so this is the interpretation of R squared. Now there is something else also here, just beneath it, called adjusted R squared. So now what it is, why we need it? Okay, so the idea behind adjusted R square is that, let me give you an example first. Let's say I create a model, model 1, from the house price data. I use the predictors area, number of, let's say, bathrooms, parking. And I build a model, its R square, let's say, comes as 0.85. I created another model using, instead of 3 predictors, let's say 5 predictors. Let's say whether it has a basement and let's say carpet quality, something like that. So more features I will add, the more variation I am able to predict of the outcome variable. So R square will always either increase or will remain the same. Let's say it becomes 0.87. Now, adding these 2 more features also add the complexity of the model. And we do not want our model to be very complex. I want it to be as simpler as possible and still giving me the reasonable accuracy. Why do we don't want a complex model? Anything complex is hard to understand, hard to explain, hard to maintain, hard to deploy, hard to make changes. So we do not want our model to be unnecessarily complex. So is adding these 2 features worth adding this much accuracy to my model? Is it worth it? That's what we want to find it out. Okay. Also, when we add more predictors, there is the problem of overfitting also creeps in, and we'll talk about overfitting once we move to the machine learning 2 module, I think. But overfitting means that my model is learning the data by heart and not learning the pattern in the data. That is the problem of overfitting. And the more complex our model is, it risks the problem of overfitting. So adjusted R square is another measurement that we calculate, which the formula is built in such a way that it penalizes the model for making it very complex by adding more predictors and then adjust the R square accordingly. So here, let's say the adjusted R square was 0.83, and here the adjusted R square will be, let's say, 0.75. It has penalizes the model for using these extra two features which were not very necessary. Okay, so according to that, it has adjusted it. So probably looking at this data, if we only look at R square, I would have probably picked this model. But looking at both, it will give us better perspective, and probably I'll go with this one, that the difference between R square and adjusted R square is not much. It means there are no unnecessary predictors in my model. Whatever is there is necessary to be there. Okay, so that's why when we are interpreting our model, we not only look at R square, we also look at adjusted R square. Whenever there is big difference between both, it's an indication that your model is too complex. You have some predictors which are not very much necessary in the model. Okay, so adjusted R square give you a more honest value to estimate the R squared for the population. It penalizes the model for using more independent variables and making it more complex. And this is the formula of it. So it is using R square, it is using the number of samples, number of the data in my data set, and it is also using the number of predictors. The higher the number of predictors, it will make the R square lesser and lesser. Okay, so that is the idea behind adjusted R square. So whenever you're looking at the result, so here our adjusted R square was 67%. So there is not much difference between 68 and 67. So this is, we consider this, it's an okay model. There are no unnecessary predictors in it. But this is the interpretation of adjusted R square. Let me ask you a few questions based upon this concept. Let me see how much you have grasped. Before that, let me see if there are any questions. I'll take those first. No, there is not. Okay, so let's try it, people. Look at this figure and give me the answer. Is it whether it is A? So this is my A, this is my B, this is my C, and this is my D. Okay, so I think everybody is giving me the right answer except a few. Somebody is saying C. C is not the right answer. So where is the RSS is more? What is RSS? People remember, it's my error. So where is the error more? Here it is. See, the lines are longest in comparison to any other model. Also, the R square is 0. So we are not able to 0% variation in my dependent variable. I'm able to predict using the predictors. Okay, so the right answer is D. Let me ask this question, and people, I need you to think deeply and then answer. Don't rush it. Similar type of questions can come in the exam. Also pay attention to this word, people. In exam also pay attention to these words. So many people are giving answer C. Why is that? C is not the correct answer, people. When we say respectively, it means that first we need to identify RSS and then TSS in this order only. B is also not the right answer. Okay, so let me explain. So let's look at the first picture. So going back to our figure in the previous slide, this is my base model. I do not have a prediction model yet. This is my actual. What is actual is Y. So this is my total variation, total deviation of actual from the base model. So this will be consider my total variation or total deviation. This is my TSS. Now come here, this is my base model, this is my predicted model. And I want to find out these green lines. And what are these? These are my explained variation, right? For this data point, I was able to explain this much. I was not able to explain this much. Okay, so all these blue lines are my explained variation. So this will be called my ESS, explained variation. Here, this is my Y bar, this is my Y hat, this is my Y. So these data points, so these lines, the yellow lines, this much variation I was not able to predict. My model is able to predict this much, but not this much. So this represents my error. And this will be my residual sum of squares. So the right answer is D. Okay, so people, you should be absolutely clear about these three terms: RSS, ESS, and TSS. Okay, let's move forward. Let's talk about another challenge that we face in linear regression. Many times when we are dealing with a real life data set, we get hundreds of predictors that can affect our output variable. As I told you, the more complex our model is, hard to maintain. So we strive for a model which is, as a general guideline, we say that any model, close to having 10, 15 predictors is considered to be a good model. Okay, so we strive for that model, but real life we get hundreds of predictors. So somehow we have to do feature selection to make our model manageable. Okay, so we have a challenge to do feature selection, or which one to pick, which one to draw. The first way of doing that is brute force method. Try all possible combinations. So let's say if we have 20 predictors, we will build a model for 20 models only with one column, then models with two columns, then three columns, trying all the combinations. So if we can build 2 raised to power 20, some absurd big number, those many models we can create and pick out the one which is having the best R square. Not a efficient way of handling this problem. So then we will do something like manual feature elimination. Here we manually do feature elimination. One way of doing it that based on our business knowledge. So we say that we know that these predictors are important, these are not, we are eliminating those. This is one way of doing that. But again, not a very efficient way. We are not applying the past data patterns into eliminating the features. Okay, so now what we do, another way is build model, then drop features that are least helpful in prediction. And one way of finding it out is if they are having high p-value. If they are having high p-value, they are statistically insignificant, not important. Now, what is this p-value? I will talk about in details. Please hold on to your queries regarding p-value. I will explain it in detail today. Okay, just right now remember, high p-value means the feature is not important. We can drop it from the model. Then we can also drop features that are redundant. Many times in our model, we have many columns which are related to each other, telling us the same story. For example, while predicting home price, house price, area and number of bedrooms, more or less, they are telling us the same story. They are highly correlated to each other. Why we want to keep both when they are telling us the same thing? Why not drop one? It will make our model simpler. So we find correlations between them and highly correlated features we drop. Okay. Now this problem, when we have correlation or relationship between different predictors, is called a problem of multicollinearity. And this creates problem in our model. Which problem I will tell you in a little bit, but one way of finding out whether there is multicollinearity in our data is using correlation matrix or using pair plot or using heat map. Like here I have given an example. Let's say we want to predict create a model which predict the sugar level of a person. And the predictors here are, let's say, the BP of the person, age, weight, BSA. BSA is body surface area. Now, we forget about the target variable. First, we look at the predictors only and trying to find out whether there are relationships among them, whether there is a problem of multicollinearity. So one way is look at their pair plot, scatter plot. So here you can see BP is related to age, not very strongly, somewhat. But here you can see BP is related to weight. So you can draw almost a straight line here. So there is a strong correlation here. It means that BP and weight are telling us the same story. Probably we can drop one of this, go with the other, thus doing feature elimination. Okay, so this is one way of dropping features that are redundant. This is one type of relationship. You can also think about relationships. Let's say BP can be find out BP is related to not only one column, it is related to, let's say, the combination of age, weight, and PSA. Now, this relationship I cannot figure out from correlation matrix. So BP is related to all these columns. So using these three columns, in a way, I can predict BP. So it is very much related to these three columns. Now, to solve this problem or to find out this multicollinearity, we use a method called variance inflation factor or VIF. Okay, so let me explain these concepts in detail. Let's talk about multicollinearity first. So what is multicollinearity? Presence of correlated independent variables in the regression model. And we don't want that. Why? Because let's say if this is my model, how do you interpret it? This is how you interpret it. If you increase x1 by 1 unit and keep everything else as constant, the y will be impacted by B1 coefficient. That is how you interpret a linear model. If you increase area by 1 unit, keep everything else, the number of bedrooms, everything else as constant, the house price will increase by beta 1 number. But when x1 and x2 are so much correlated with each other, we cannot keep x2 constant while changing x1. Because of this, the coefficients become non-interpretable. Okay, so in case of multicollinearity, we cannot keep them constant, and interpretation or coefficients become a problem. And also, when we have relationships like this, let's say x1 is equal to minus x2, it changes the beta signs arbitrarily and the model is not very interpretable. For example, it can give something like this. House price is equal to, let's say, beta naught minus beta 1 into area. And you wonder, as the area increases, the house price decreases. So, if you find this type of problem, it means that there are some correlated predictors with area which are negatively related to area. Because of this, the beta signs are changing arbitrarily. And also, in multicollinearity, increase model complexity. The more predictors will be there, hard to understand the model. Okay. To solve this problem, again, we can check, we can do correlation, we can find out correlation. That is one way. Another way is using VIF. Correlation only gives you relationship between two variables. VIF will give you how one predictor is related to all the other predictors. And its formula is 1 divided by 1 minus r square. But this is not the r square of your model, but the r square of the various models created using only independent variables. For example, if I have 3 predictors for my model, let's say beta 1 x1 plus beta 2 x2 plus beta 3 x3. To check the multicollinearity among them, what do? We create number of models. Okay, so the first model that we create looks like this. X1 is equal to alpha 0 plus alpha 1 x2 plus alpha 2 x3. In a way, I want to find out, can I predict x1 using x2 and x3? How accurately I can predict? Let's say the r square comes here 10%. Then I build another model. I will keep x2 as independent variable, as dependent variable, and I build another model using this type of equation. Let's say it comes as 20%. And then I finally build my third model. I'll keep x3 as dependent variable and then build another model using x1 and x2. Let's say that comes as 80%. How do we interpret this? I will interpret this that x1 and x2 together can explain 80% of the variance of x3. It means we can pretty much predict x3 from x1 and x2. Okay, so x3 is considered to be redundant and can be dropped from the model. Now, based upon these r square, we calculate VIF, which is equal to 1 minus 1 minus R square. And it comes as 1.1, 1.25, and 5. And we have a guideline that any variable with VIF greater than equal to 5 is considered as highly multicollinear and can be dropped from the model. Okay, so that's why whenever we are building a model, we check the VIF values of all the predictors. Anything more than 5, that predictor can be predicted from the other predictors, so we can drop it. Okay, so VIF, or the variance inflation factor of 1, means that there is no correlation among the particular predictor and the remaining predictor variables, and hence the variance of that predictor is not inflated at all. So if it is VIF is between 1 to, let's say, between 1 to 4 or less than 5, we will keep that variable. Anything more than 5, we can drop it. Let's say if we run a model and we get VIF of 5 predictors, more than 5, you can drop those 5 predictors, but one by one. Never ever drop multiple predictors at a time. Always drop it one by one, because when you drop one, this whole calculation of VIF will be recalculated. And probably it will give you another different VIFs now. Okay, so always drop it one by one. So this is the way to solve multicollinearity. Okay, so either we can use correlations or we can use VIF for that. Once we drop the predictor, rebuild the model, repeat till you get the ideal number of features. And the last one, we can also do automated approach. So manual approach we can still do when we have manageable predictors. Let's say 20 to 30 predictors. We will look at the VIF for all those predictors, try to remove one by one high VIFs, and then probably restrict our model to 10 to 15 predictors. But when we have, let's say, more than 100 predictors, then doing manual feature elimination becomes very difficult. So we need some automated way, and there comes the concept of recursive feature elimination, or RFE. Let me explain that to you also in detail. Okay, so what do we do in RFE? RFE can use many techniques. The most common ones is using, so RFE, what is it does? In RFE, elimination is based on the magnitude of coefficients. You know that the higher the coefficient, the more important that predictor is, the more, that predictor is more important in predicting the target variable. Okay, so we only find features which are having high coefficient. We will eliminate which is having small coefficients. Okay, so let's say we have a model, we have to create a model, let's say using these 6 predictors. We want to use RFE to get top 3 variables. Okay, and we use recursive, so RFE stands for recursive feature elimination, and I will use one flavor of this. We use a backward elimination technique. There is forward also and a mixed also, but most of the time we use backward elimination technique. What do we do in this? The first step is create a model with all the features. Okay, so it will create something like this: beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus beta 5 x5 plus beta 6 x6. Then we find the, let's say here the beta 3 is the smallest one. So what we will do, RFE will eliminate that independent variable for which the coefficient is minimum. Because we consider that is not very much related to the target variable, that is not contributing much, so that is a candidate to be dropped. Then recreate the model with left out features. And then we repeat these steps until we are left with 3 independent variables. So when we apply RFE technique, we have to give it, whenever we say RFE, we have to give how many variables you want. So top is equal to how many variables you want. Here we wanted 3. So that will only give you the top 3 variables. Okay, so this is the idea behind automated approach. So here we give me top 10 features and then pick those. But again, even after picking features with RFE, you still need to check VIF of those for multicollinearity and also check the correlation between them. Okay, so RFE does not guarantee solving multicollinearity. So even after RFE, we have to check VIF for all the predictors. Many times we go with mixed approach. How? Let's say if we have more than 100 predictors, first we will apply RFE and get the top 30 features and then do the manual elimination using our domain knowledge, using VIF value, using P value, using correlation. We eliminate manually, let's say 10 more features. And then we will end up with, let's say, 15 predictors. Oh, 20 predictors, something like that. Okay, so many times we go with the mixed approach also. Okay, so these are the ways of doing feature selection. Let me see if there are any questions. I'll take those. Sagar, ESS is explained sum of square. How much deviation we were able to explain. Okay, so going back, let me explain that. Many people are asking this, so let me. Okay, so ESS is, if we go with this, okay, this is my ESS. How much deviation I was able to explain from the total deviation. Okay, so this is my base model, this is my total deviation. This much deviation I was able to explain, this much I was not able to explain. So this is my residual and this is my ESS. Explained deviation, unexplained deviation. Okay? Hope this is clear. Lokesh is asking which method is best to solve multicollinearity. So Lokesh, we have to check both the methods, correlation matrix also and VIF also. Shovik is asking, after using VIF, if we create a heat map, will we find features that show high correlation coefficient? Can we use both VIF and heat map? Yes. Shovik, I said the same thing. You have to use both. One gives you relationship between two variables. VIF gives you relationship between one predictor variable and all the other predictors. Pavak, RF is conducted after the model is built. Yes, so RFE itself does a lot of iteration and create models and then give you the top 3 or top 5 predictors out of it. This is done as a pre-processing step, not after building the model. In itself, RFE builds a lot of model, but that is something in the background is happening. For us, RFE is a pre-processing step. After eliminating unnecessary features using RFE, then we go ahead and build the model. Mithali is asking, why are we doing this process after test train split? Why not before that? Mithili, no, RFE, VIF, we are doing before split. Only scaling we do after split. So all this is done before the split. Sriram is asking, can RSS be below the predicted Y line? Can RSS be below the predicted Y line? Does it depend on how we calculate this baseline, right? Yes, Sriram. So if you go by this, so here, this is my ESS, right? This is by base model predicted this. I predicted this. Base model predicted this. I predicted this. This was my actual. So this much deviation I was able to explain, this much I was not. This will be called my residual and this will be called my explained. So it can be below the line also. So, you can pick one point and then think about that point. I think you will get it. Okay. Similar thing pattern can be down also. Okay, great. Preetham is asking, if we use RFE and manual feature selection before split, then we will end up peeping the test set. It's okay. It's okay. Still okay, Preetham. We are just trying to find out the best coefficients. Okay, so again, you will say that even VIF we should do after split. No, for the scaling, ideally, yes, test data set should not be available even for pre-processing, but it's a normal way is we do VIF, we do RFE before the split. After the split, we only do scaling. But that's a good point, good observation. Okay, I'll think about it, what problems it can create if we are doing RFE before the split. So in the async material, anybody remembers in the code, are we doing RFE before the split or after the split? Before the split. Oh, some people are saying before, some people are doing after, saying after. After. So more people are saying after. Okay, yes. So that you can do that also, what we can do, we can first do the split so the test data does not peep up while creating models in the RFE. So we can do that also. I think that will be a better option. Yes. So after, sorry if I said before, now I have rethought. I think it should be after. Ideally, these days we have so much data, we deal with three types of, we split it in three types. One is like a holdout data, which is, never visible to the data set, only after creating the final model. And you will learn about that, probably, learn that holdout strategy also, I think in one of the modules. Okay. So after split, we will do yes, holdout is for validation set. Okay. So generally, what we do when we have a lot of data, okay, we divide our data into three sets. One is called validation set. Okay, people use different terminologies. I'm just using it here. So this is my train, this is my test. So we only use, the whole data for, for the RFE, VIF, everything. We pick something, we tune our data model here, and finally we test it on the validation test, so that our model can never see the validation set. Okay, so that is one type of strategy that we can use. These days we have huge amount of data, we can afford that. When we have small amount of data, then there is a problem, we cannot divide it into three sets. But final, we're going to use RFE and VIF after the split. Okay. So let's move forward, people. Okay, so now let's move to another important concept called p-value. Now you will see two type of p-values in the model. This is the p-value for F statistic, and these are all the p-values. Now, what do they signify? Let's discuss that. Before that, let me explain to you what is a p-value. This is the most confused topic I think many people see in statistic. And let me try to explain this with a story today. Let's see, probably you'll remember it for a long time. So let's say there was a professor, there were 3 research scholars working under him. They share professors, responsibilities. Sometimes they teach, assist them in teaching. Sometimes they do administrative work for them. Nobody likes to do administrative work. So they decide who's going to do it, A, B, or C. They made a strategy that they asked A to create 3 chits with everybody's name on it, put it in a box. Every Monday morning, professor will come, he picks up the chit, whosever name will be there. He will do the administrative work for 1 week. Next Monday comes, professor picks up another chit. So they put the chit back in the box. Professor picks up another chit, whosever name is come will do the work. Let's say the first Monday came. Professor picks up the chit. The A's name was not picked. What do you think? What is the probability of this happening? What is the probability that A's name will be picked? 1 by 3. What is the probability A's name will not be picked? 2 by 3. 66% chance. Fair enough. Second Monday came. Again, the A's name did not come. What is the probability of that? 2 by 3 into 2 by 3. 2 by 3 raised to power 2. It comes as around 42%. Still okay. There is a chance of that happening. 12 weeks happened. A's name did not come. What is the probability of that happening? 2 by 3 raised to power 12. 0.77%. Less than 1% chance. Okay. So now B and C, they begged the professor to open up the box and see whether A's name's chit is there or not. Okay, so what did we do today? How do we relate it with hypothesis testing? So B and C made a hypothesis in the beginning. What was the hypothesis? A is honest. So in statistical term, we say that they made a null hypothesis. A is honest, which is a status quo, which is, as the process is, it is. In statistic, we create null hypothesis and then we create an alternate hypothesis, which is A is not honest. We cannot prove A is honest, but the evidence that show that is before us, 1% chance of A's name did not come, the likelihood of that happening is so low that it raises doubts in our mind about the null hypothesis. The evidence is against the null hypothesis. So when we see this type of probability, we reject the null hypothesis and accept the alternate hypothesis. So we will conclude that based upon the evidence on hand, we conclude that our null hypothesis is rejected. Same way we do in statistic. Okay, so in the very first week when the probability is high, 66%. Okay, so the evidence is showing that the chance of looking at this evidence, it's likelihood 60%, 66%. So we keep accepting the null hypothesis. But as soon as it goes below some threshold, and we have defined that threshold as to be 5%. Statisticians have defined it. So this probability is called p-value. So p-value is the probability of observing this sample data. So we were observing this data happening when null hypothesis is true. If the probability is high, it means our null hypothesis is still true. But when the probability goes low, it raises doubt in our mind about the hypothesis we have made. Otherwise, we would have never gotten this low likelihood. Something must have changed. Okay. So similarly in statistics, we make assumption about the population tested using sample data. If probability of seeing that sample data is high, null hypothesis is true. Okay. Or less than 0.05, null hypothesis is rejected. Statistician does not like this term, null hypothesis is true, because they are very finicky. They will say that null hypothesis is true only when we have studied the whole whole population. Okay, so instead of saying null hypothesis is true, they say that we have failed to reject the null hypothesis. Because we were failed to reject it, we have to accept it, right? So the diluted version is null hypothesis is accepted. But they like to call it failed to reject. Okay, and we have this mantra, P low, null go. Means if the P value is low, the trust in our null hypothesis go away, and we will reject the null hypothesis. P low, null go. Okay, so how do we apply this concept here? So here, similar way, every p-value has a null and alternate hypothesis attached to it. In this scenario, the hypothesis is, this is a test to check overall model validity. So we start with the question that our predictors cannot predict the output variable. There is no linear relationship between the predictors and the target variable. So our null hypothesis starts with all the betas are 0. And my alternate hypothesis is at least one beta I is not equal to 0. In statistics, we also called as ANOVA test, which use F statistics. But you need not to worry about that. Okay, just understand this. This checks the overall model validity. We start with the question that our predictors are not linearly dependent on, linearly related to target variable. So all the predictors coefficients are 0. So they cannot predict the target variable. And alternate is at least one is not 0. And then we check the p-value for this test by creating some calculations. Okay, if the p-value, so what is the p-value here? P-value here is 2.73 divided by 10 raised to power 84, which is 0.00000000. So to see this sample data, which we are seeing about the house prices, the likelihood of getting this data is 0% if my null hypothesis is true. So it raises doubt in our mind about the null hypothesis. We reject it and we accept the null hypothesis. So here we will say that statistically overall model is valid. That is the significance of this p-value. So we start with the question, is there at least one independent variable linearly related to the dependent variable? This is my null hypothesis, this is my alternate one, and we compare it with 5%. If it is less than that, it means that the confidence in null hypothesis 0%. 0% confidence, 0% chance of this thing happening. So we will reject it and accept the alternate one. This was about this p-value. Okay, now the similar concept is there for these p-values. Now we run many tests and create many p-values for each predictor. Again, every p-value has a null and alternate hypothesis. For this, the null hypothesis is that this area predictor is not important predictor. With using area, you cannot predict house price. Okay, so we start with null hypothesis, beta 1 is equal to 0. And our alternate is beta 1 is not equal to 0. No, it is an important predictor. Then we run something called t-test here. So we find out t-stat using t-test. We find out the p-value. What is the p-value here? 0.00000 some percent, which is less than 5%. How do we interpret it? The likelihood of getting this data in this house data set, the likelihood of seeing this area data, given that beta, my null hypothesis is true, the chance of that is 0%. So it means my null hypothesis cannot be true. We reject it, except our alternate hypothesis, which says beta 1 not equal to 0. So from the sample data, we are doing test for the whole population. So for the whole population, beta 1 is not equal to 0. So that means that we can use area predictor to predict the house price. So this is a good predictor. This is also good. So anything less than 5% is considered to be a significant predictor. So here everything is good. If you find a few predictors more than 5%, it means that they are not significant. In their case, we are accepting the null hypothesis. Beta 1 is 0. They are not significant. We go ahead and drop those variables one by one and then build the model again, and again. Okay, so this is how we check the significance for coefficients. Okay, so when we are looking at a linear regression, its output, we need to check all of these things. R squared, adjusted R squared, there should not be a big difference between them. This p-value should be less than 5%, means the overall model is validity is true. Then we check all the p-values of each coefficient. All of these should be less than 5%, making each predictor as significant, statistically significant, and then finally we check the VIF, which looks for multicollinearity. All the VIFs should be less than 5. If all these checks are in place, we can go ahead and create that model, because that is satisfying all the requirements. Okay, so with that, let me see if there are any questions related to this. Sai is asking here, H0 is insignificant and H1 is significant. Right, so Sai, we don't use these terms. A statistician will not like it. They will say that here the predictor area is significant. Here we will reject the null hypothesis and accept the alternate hypothesis. This is the language that they use. They say that the predictor is significant or not. Yes, for understanding, yes, you can think it like that. Okay, but do not use this as as an official language when you are creating PPT or presenting into stakeholders. Anybody who has statistic knowledge, they will not accept these wordings. Okay, but for your understanding, go ahead, understand it like that. And I strongly recommend that you make notes of your own with your own hands, especially for the concepts like p-value and thing, because 2 months down the line, you will again forget it. So it's always a good idea to make notes of your own. Yes, Shikha, lower the p-value. In this scenario, better it is for us. We keep rejecting the null hypothesis, which says that nothing is significant, no predictor is linearly related to the output variable. Great. And I know that you have not gotten this thing fully 100% because most people do not get it. I strongly recommend to go through this web recording one more time to understand the p-value and then make notes. Mandira is asking, can we drop multiple predictors with high value in one go? No, Mandira, no. Because all these calculations are recalculated every time you drop something. So that's why you cannot drop multiple predictors at a time. Always do one by one. Let's say you will find there are 3 variables which are having high p-values. There are 4 variables which are having high VIFs. Start with any of those, but one by one. Okay, great. So let's answer these questions and then we will take a 5-minute break. Okay, so question number 1, please go through it and let me know the answer. Please write it like this, everyone, 1A or 1B, 1C, 1D, so that I know it's an answer of question 1 or question 2. Okay, so the right answer is, so I'm getting a lot of correct answer. Yes. Okay, people, A and C is not correct. The right answer is slope. This is from our geometry, everyone. So let's say we have this line. This is my y-intercept. If I increase x value by 1 unit, it's going to increase it by this slope. It's going to increase the y with this slope. Okay, so the right answer is by its slope. Let's answer the second question. Okay, so let me see what is the right answer. 2b, no, not correct. People, it can't be 2b. The slope is negative in 2b. If my linear regression model would have been this, then it is the negative slope. For this, the right answer is positive slope. As x increases, y is also increasing. So the right answer is A. Okay, let's go to the third question, everyone. Yes, the right answer is C. So you see, there is no perfect correlation here. There is correlation, right? As if it is, what is 0? If the line would have been this, then it is 0. Okay, if the line would have been like this, then it would have been minus 0.88. 1 would have been like this. All the data points and perfect correlation. Okay, so the right answer here is 0.88. Okay, people, so the right answer is 78.3. We cannot have r square as negative. 0.0 r square means that we are not able to explain the variation at all. So it is like we have this type of data, okay, for 0.0, okay, and 100% means again we are able to explain everything. Again, this type of situation. So the right answer is 78.3. Also, in case of simple linear regression, where we have only one predictor, if we calculate correlation coefficient, okay, you people remember correlation coefficient is also represented as small r. In case of SLR, r square is simply the square of this correlation coefficient. So here, if you do a square of 88, it will come as 78.3. Okay. With that, people, let's take total variation explained. Let's, Rajmohan. So, oh, it's a total variation explained. It's not r square. Yes, you're right. So we consider it 78.3. This is just another information. Here we are not looking for, here it is not a square of 88 because we are not saying r square. We are saying total variation explained. Okay, so, but again, the r square in this scenario will be the square of 88. 0.88. Okay, but you are right. This is the total variation. This is our guess. Okay, so with that, people, let's take a 5 minutes break. Grab your coffee or tea, and then we will continue with the topics. Let me take the last question. Mithli is asking, what if the VIF value is less than 5 for a variable but high p value? Should we drop that? Yes, Mithli. In order to make the cut for a predictor to be in model, it has to satisfy both conditions. P-value less than 5%, VIF less than 5. Okay, let me share my whole screen and let's do 5-minute countdown. Okay, so people, see you in Okay, welcome back everyone. Let's do a quick audio and video check. Please say yes in the chat window if you are able to hear me and see my screen. Great. I'm getting a question here. Sandhya is asking, is it necessary to do a correlation check before RFE? Sandhya, you should understand the difference between correlation check and RFE. Correlation check will give us the relationship between two variables, and RFE will give us the relationship between one predictor and all other predictors, and we have to do both the checks. Great. Okay, so let's move forward, everyone. Let's move to logistic regression. Okay, so logistic regression is another extension of linear regression. Okay, it is used for classification problem. And we have two types of classifications. One is called binary, where we want to predict only two things, let's say 0 or 1. Okay, 0 stands for no, 1 stands for yes. Let's say this is good, this is bad. Okay, this is not churn, non-churn, this is churn, and so on. And then we have a multi-class classification also, which is 0, 1, 2. For this module, we are focusing only on binary classification. So how it is an extension of linear regression? What is the output of linear regression? Y hat is equal to beta naught plus beta 1 x. Now what we want the output from logistic regression? We want to predict the probability of somebody being a 0 or 1. So probability of 0 or 1. So we have to do some type of transformation going from linear to logistic, and that transformation is called sigmoid function or sigmoid transformation, or it's also called as logit transformation. Okay, the output of LR varies anywhere from -infinity to infinity, but output of logistic regression varies only between 0 and 1. And we have a threshold value. Okay, so threshold says that threshold value we apply, which means that if the probability is less than 50%, we assign it 0. If it is greater than equal to 50%, we assign it as 1. And the sigmoid functions looks like this. Okay, so here, this is our linear regression model. Let's say if we want to fit that into our classification problem. This is the blood sugar level, this is the diabetes, and y-axis is the probability that varies between 0 and 1. One problem with linear regression is this line can be extended above 1 and below 0, giving us values which are not correct. Okay, so predicted y can exceed 0 and 1 range. And the second problem with this is the errors. See, the errors are too much. Error is too much here. This line is very far away from the points, so the residual will be high. So we will change it to sigmoid function, and we get this line. This function gives us the value. It will never go beyond 1 and never go below 0. Okay, and as you can see, the errors have also reduced. So this line is much closer to the points in comparison to this linear regression. And this sigmoid function has an equation which is goes by this 1 divided by 1 plus e raised to power minus beta naught plus beta 1 x. Okay, so this is the equation of sigmoid function. Let me take a question. So Uday is saying, how can we check correlation when number of predictors are more than 100? Yes, Uday, you're right. So what you can do, probably run RFP first, reduce it to some number of predictors, and then check the correlation. Okay, here we are checking correlation among predictors, not with target variable. Sriram, you can also do that. You can check the correlation of all x variable on y. It will give you an idea that which variables are most related to y, and probably those are the important ones. So these are two different concepts, right? Checking the correlations among predictors and checking the correlation between y and predictors. Great, let's move forward. So we were talking about sigmoid function. Now, logistic regression also has a concept of odds. Let's talk about that. What is an odds? Odds is P divided by 1 minus P. What is the odd of India winning? Let's say the probability of, oh, I'm sorry. So, hold on a second. Okay, so odds is equal to P divided by 1 minus P. So what is the odd of India winning? Let's say the probability of India winning is 0.8. Then the odd will be 0.8 divided by 0.2 is equal to 4. What does it mean? The odd of Team India winning the match is 4-1. So if they play 5 matches, they will win 4 of them. That is the odd. Okay, so similar way, so this equation P of diabetes, it's actually is equal to y is equal to 1. Y is equal to 1 means P is having, the person is having a diabetes given X. We can also write it like this. It comes as 1 plus e raised to power minus beta naught plus beta 1 X. If I want to find out what is the probability of y is equal to 0 given x, you can write it 1 minus probability of y equal to 1 given x. And if you fill out this information here and solve it, you will come with this formula: beta naught plus beta 1 x divided by 1 plus e raised to power minus beta naught plus beta 1 x. Okay, and if we do the odds of it, P divided by 1 minus P, and you solve this, you will get something like this. And if you take a log of this, it will come like this. So we have this linear line equation here, which is equal to log of odd ratio. Okay, so how do you interpret it? Okay, this is how you interpret it. If x is increased by 1 unit, log odds will be increased by beta 1 units. Okay, in a sense, the odds of y is equal to 1 will be increased over y is equal to 0. Okay, so if beta 1 is positive, if we increase 1 unit of blood sugar level, let's say, okay, the log of the odds of person having diabetes will increase over not having diabetes. Okay, or more or less in diluted form, you can say that the probability of a person having diabetes will increase if we increase the value of x by 1 unit. And we can interpret these coefficients the similar way as linear regression. The higher the coefficient will be, the more it will affect the probability of diabetes. Okay, this is the interpretation of log odd ratio. Okay, yes, sorry, it will be. Okay, and then you can extend this formula to beta 1 x1 plus beta 2 x2 plus beta 3 x3 for the multiple predictors. Okay, let me just fix this. Okay, so I will say probability of y is equal to 1 given x is equal to 1 divided by 1 plus e raised to power minus beta naught plus beta 1 x. And for multiple predictors, we have this formula. Yes, so Shikha, how do we interpret it? As we increase the value of x by 1 unit and beta 1 is positive, the odds of y is equal to 1 increases over odds of over y is equal to 0. In the sense, probability of y is equal to 1 increases. Not by beta 1, but the odds of y is equal to 1 over y is equal to 0 increases. Okay, and in a diluted version, you can say that as you increase x, the probability of y is equal to 1 increases. That's a diluted version. The probability of y is equal to 1 increases. But this is the official definition. So y is equal to 0 means no diabetes. And y is equal to 1 means diabetes. So the probability of person being diabetes increases as we increase the value of x. Okay, great. Now let's talk about the cost function here. Remember how we get the best values of beta 1 and beta 2? It comes from the cost function. If you remember what was the cost function of our linear regression, it was the RSS. So we wanted to minimize I is equal to 1 to n y minus y hat square. Similarly, let's talk about the cost function of logistic regression. So what do we want to minimize or maximize here? So if you look at this figure, for blue points, I want this line to be very close to the blue points. Okay, so I want these lines, and these lines, let's represent the probability value. So I want P7 to be maximum. I want P8 to be maximum. It will be closer to the blue points. P9 to be maximum and P10 to be maximum. But on the other side, I do not want P5. I don't want this P6 to be maximum, right? P6 is for red line. So I want this P6 to be minimum. I want this P5 to be minimum. Okay, so some are maximum, some are minimum. We cannot have a cost function mixed one. So what do we decide? Instead of minimizing P6, we can achieve the same thing by maximizing 1 minus P6, by maximizing 1 minus P4. Okay, so if we take it for all the data points, we want to maximize for all the blue points, we want to maximize P7, P8, P9, 10. And for all the red points, we want to minimize the 1 minus P1, 1 minus P2, 1 minus P3, and so on. Okay, so our cost function becomes maximizing likelihood, which is again 1 minus P1 into 1 minus P2 up to 1 minus, let's say, P4, P7, P8, P9, P10. If we take log of this likelihood, okay, again, we are maximizing this. I'm introducing log here, so I will introduce log here also. And you know that in mathematics, when you do log AB, it means log A plus log B. So make it simpler, product becomes difficult. So what we do log of 1 minus P1 plus log of 1 minus P2 and so on. And then we create that we want to maximize two formulas, log of 1 minus Pi where these are for zero variables, okay, plus I is equal to, let's say, m plus 1 to n, where log of Pi. And then we put the values here. So I will put what is 1 minus Pi, 1 minus 1 divided by 1 plus e raised to power minus beta naught plus beta 1x. This is for zero, the points with zero label, and this I will do 1 divided by 1 plus e raised to power minus beta naught plus beta 1x. And then we use an optimization algorithm similar to gradient descent to maximize this cost function maximize this function, and that will give us the best values of beta naught and beta 1. Similar way that we have done in linear regression. Okay, so the cost function, which the function that we want to maximize in logistic regression is the likelihood, log likelihood actually. Okay. Sumer is asking, do we need to know these cost function formula by heart for the exam? No, Sumer, this is just to give you an idea. Nobody asked you a question, only the interpretability should be clear. Only conceptually, okay? Define likelihood. So likelihood is this. It is the product of all the probabilities. For ones, it's a simple multiplication of probabilities. For zeros, it is 1 minus probability. The graphical part, yes. So see, this is the line. There can be many lines that can be created, right? You can create line like this also. Now, which line will be the best fit line? To find it out, we use this cost function. Okay, and we either need to minimize something or maximize something to find out the best line. So here we have decided that we're gonna get those lines where these p's are maximum. For ones, these p's. For zeros, the 1 minus p's. That's where the concept comes, and we just use this formula. Then we plug in beta naught plus beta 1 x. Then we use an optimization algorithm to find out the best values of beta naught and beta 1. So P5. So we are missing a value there. So let me. So this we are missing a point here. Okay. So let me. Okay. So P5 is this point, people. So I made it incorrect. Okay. So for P5, we want to maximize 1 minus P5. We want to, I'm sorry, we want to minimize this one. We want to maximize this P5. Because, you know, the corresponding point is this. So we want to maximize this. We want this line to be very close to this point. So we want to maximize the P5. Okay, great. Okay, so the main thing from logistic regression is it gives you the probability, it returns the probability, it predicts the probability. The cost function here is maximize log likelihood. These are some of the conceptual questions that you should remember. Okay, and then you have this threshold value. I will put it elsewhere. Okay, so don't worry about it. Okay, so the questions can come to find out the odds. Okay, so that should be clear to you. So let's try to solve a few questions. Okay, so what is the answer, people? Sai is asking the output of logistic regression continuous or category. Sai, the right answer is continuous. That's why it is considered as an extension to linear regression. So here output is still continuous in nature, but it has some limitation. It has to be between 0 and 1, and it gives us the probability of that variable. Probability of that data point to be 1. Probability of person being diabetic. Okay, hope this is clear, Sai. Great, yes. So people, the right answer is B. So how do you find out? You use this formula P divided by 1 minus P, which is 0.7 divided by 1 minus 0.7. So the right answer is 2.3. Let's solve one more problem and then we will move to evaluating the model, which is the important concept in logistic regression. Okay, so here it will be 0.3 divided by 1 minus 0.3. So the right answer is 0.42. Okay, now the most important concept in logistic regression is evaluating the model. Because in linear regression, we only check accuracy, but here we not only check accuracy, we check other things also. Okay, like confusion. So we create a matrix called confusion matrix. It shows the ways in which your classification model is confused when it makes predictions. Let's understand this matrix in detail. This matrix looks like this. It's a 2 by 2 grid. Let's understand this. So if you go from here, this is telling you the truth because we have actual data from the past data. So we also know the truth. So this is the truth and this is what we predicted. Let's say positive means 1. Let's say the person was diabetic and truth was he was diabetic. Our model predicted him as diabetic. We made the right decision. This data point will be called as true positive. We predicted positive and it was true positive. Let's say the truth was that person was not diabetic and our model predicted as not diabetic. We made the right decision. The model predicted it to be negative and this was the truth. So everything is fine. Let's say the truth was the person was diabetic and we predicted the person to be not diabetic. We made a mistake. We predicted the person to be negative, which was false negative. Then the truth was the person did not have diabetes. We predicted the person has. We made the wrong decision. We predicted the person to be positive and it was false. So we call it false positive. Now, based on the model that we create, the tool can automatically create this type of confusion matrix that how many times actually the person was diabetic and we predicted as diabetic and vice versa. So let's take this example. Let's say I want to build a prediction model to predict whether a person is having COVID or is COVID positive or not. based upon his symptoms or his vitals and all of that. So here is the truth, and here is my prediction. Now, what is the accuracy of this model? Let's say we will only look at the accuracy. What is the accuracy? Accuracy is how many times we have predicted correctly. So accuracy is equal to my good decisions, TP plus TN, divided by my all decisions, TP plus TN plus FN plus FP. So which will come as 100 plus 900 divided by 100 plus 900 plus 100 plus 5, which comes as 1000 divided by 1105, which comes closer to 90%. 90% accuracy, best model. Hold on a second. In linear regression, this could have been worked, but not in classification model. Because here, let's say, what is our requirement? Our main focus is do the detection rate. To detect that we are predicting correctly and we are detecting all the COVID patients. Okay, so we want to check what is our detection rate. And what is a detection rate? Detection rate should come that how many people who were actually infected, how many of them we were able to detect correctly. So how many were actually infected? 200. How many we were able to predict correctly? 100. So detection rate here will be how many were totally infected, the truth, TP plus FN. And how many I was able to predict correctly, TP divided by TP plus FN, which will come as 100 plus 100, which comes as 50%. This is a bad model. We were only able to predict 50%, detect only 50%. Imagine the damage that has been done. These 100 people which go undetected can infect hundreds more people, 100 of people. Okay, so this prediction model will not be a good one. So when our FN, so this was my FN, when my false negatives error is costly, then I check detection rate. And this detection rate is also called as recall or true positive rate or sensitivity. So whenever my FN error is expensive, as in this case, I not only check accuracy, I also check recall. And it changes from situation to situation. Let's take another situation. Here we are building a prediction model to predict whether a person is guilty or not based upon some predictors. Okay, so this is the confusion matrix for it. Let's check the accuracy first. It will come again 100 plus 900 divided by 100 plus 900 plus 90 plus 10, which will again comes as 1000 divided by 1100, which will be equal to 90%. Okay, now check the detection rate, which is the recall. What it is TP divided by TP plus FN, which comes as 100 divided by 110, which is again closer to 90%. Very good model. No, hold on a second. Let's look at which error is more costly here. As per the judiciary system all over the world, we go with this motto: let 100 guilty people go free, but not a single innocent person should be put in jail. That is the motto that they follow. So here there were 110 guilty people. 10 people who were guilty, we set them free, which is okay. But look at this, there were 990 not guilty people actually. 900 we predicted correctly, 90 innocent people we sent to jail. So here, recall will not be the best metric to figure it out. We use something called precision. Precision is how many times when we said once, actually those were once. Okay, so precision will be calculated as TP divided by how many times we said guilty. They were actually guilty. So it will be 100 divided by 100 plus 90, which is 100 divided by 190, which comes as, I think, around 55%. So it's a bad model. So when FP is costly error, we go by precision. We look at precision. Rest, there are F1 score and all those things, but these are the two important evaluation metrics that you should be very clear about and where to use which one, because it changes from situation to situation. Which error is more costly, accordingly we'll go with whether by precision or by recall. If both are important, we go by something called, I think, F1 score, which is like 2PR divided by P plus R, which is P is precision, R is recall, something like that. Okay, so please pay attention to these one. Let's solve one question. Rest you can do it on your own. I just want to give you an idea that these type of questions can also come. Okay, so let me say, so given a confusion matrix, you should be able to find out the accuracy, precision, recall, and the F1 score. Solve this question on your own. Okay. Shovik is saying, for a multi-class classification, how can we evaluate recall? So Shovik, for multi-class classification, it's a whole different world. There we cannot use logistic regression. We have to use some other algorithm, probably, I think you can use the KNN algorithm or somebody else. So logistic regression is only to solve binary classification, and the evaluation matrix are also different for multi-class classification. Okay, that's a whole different beast. Great, but many real life problems deal with binary classification. That's why the logistic regression is very popular for binary classifications. Okay, let's move ahead, people. I think you can solve this pretty easily. Let me talk about one more metric called ROC curve, or we calculate AUC, area under the curve. Let me first give you how do you create this diagram. R is just a random model. What is a random model means? Let's say we have been given predictors, but instead of using that predictor, if we want to predict whether a person has diabetes or not, I flip a coin, 50% chance of diabetic, 50% chance of non-diabetic. It's just like flipping a coin. Okay, no knowledge in this. Okay, so that I consider as my base model, and anything I build better than that will be compared with this base model. Okay, so then what we do, we create this data. So we have a model will give you the probability will remain the same. Now according to that probability, based on threshold value, so let's say I took the threshold value as 50% first. According to 50%, I assigned zeros and ones, and then calculate true positive rate, which is our recall. And I calculate FPR, which is 1 minus precision. I think specificity is precision. No, that is a true negative. Okay, so no, FPR is 1 minus, yes, so I think it is 1 minus precision, FPR. No, specificity is something else. So there is a formula for FPR. Just remember, it's a false positive rate, the error that we made. Okay, so threshold, let's say TPR comes as, I don't know, TPR comes as 80%, 0.80, FPR comes, let's say, at 0.2025. It can come anything. Then I change the threshold value. I make it 10%. So anything probability less than 10% will goes in 0. Anything more than 10% goes in 1. Then I calculate the TPR. Let's say it gives us some other value. I'm just making up these numbers, everyone. Then I do 20%. Then I do 30%, and so on. I keep on going. This will give me these points. Then I plot my FPR on the x-axis and TPR on my y-axis. Then I plot these points and join them. This will give me this ROC curve. Now, what is my objective here? I want TPR to be maximum and FPR to be minimum. So where it will be? In this area. Here, if you can see, the TPR is maximum and FPR is minimum. So this is my goal. So I want this line to be as close to this corner as possible. And if this is closer to this area, the better will be my model. I also have a way of calculating area under the curve. This is called AUC. So the metric, instead of looking at this figure, we calculate a metric here called area under curve. The more the area under the curve, it means this line is more closer to this corner, and the better will be our model. So this is another model evaluation technique for classification model. Let me take a pause here, and please let me know if you have any question related to this. So Shikha, the corner concept. So here in this corner, we are having high TPR, which is my true positive rate, which is my recall detection rate, which I want to be maximum, and low FPR, which is my false positive rate. Again, false positive, you can imagine it's my error, and less error I want to make. So this is the corner which is where I want my line to be stretched to. So this is my objective. So the closer this line to this corner, the better TPR there will be, the lower FPR there will be. And the area will also increase accordingly. So we measure this not by looking at this figure. We can look at the figure also, but we calculate this area under curve metric and compare different models based upon this value also. So Manumit, if you want to increase AUC, again, it is just a metric. You have to improve your overall model. It means your probabilities are not correct. Probably you are, you need more data, you need to derive more matrix, you need to fine tune your hyperparameters, you have to include more predictors. There can be number of reasons by using which you can increase the accuracy of the model. This is again the accuracy, how accurately we can predict, how much less error we have to make. Okay, hope this has cleared your doubt, Manumit. Mithli is asking, do the model needs to satisfy both the conditions? Which one takes priority? Mithli, which both the conditions? If you're talking about TPR and FPR, we want both, okay? So this gives you an idea about where both these things are important. Raj Mohan is saying, so for every threshold value, there is different curve plotted. No, Raj Mohan, for every threshold value, a different data point is plotted. This cross is one threshold value. This cross is for 50%. This cross is for 10%. This cross is for 20%. So for different threshold value, we get these points, 0.80, 0.25. And then we will plot it and join it. So for all threshold values, we will get only one graph. High TPR and FPR and AUC. So Mithli, this is the same way of looking at, different way of looking at the same thing. Okay. So AUC is equal to high TPR and low FPR. This is another formula which integrate both of these things, high TPR and low FPR. Shriram, threshold value. Remember what is a threshold value? Sorry. What is a threshold value? Remember? So we have this type of sigmoid function and it gives us a value between 0 and 1. If the value comes as 0.8, this is my threshold value, which is by default as 0.50. So if we get a probability as 0.80, I will assign it the target variable as 1. If I get 0.40, I'll assign it 0. Okay, now this threshold value can be changed. I can make it 10%, I can make it 20%, I can make it 90%. And then accordingly, the assignment of 0 and 1 changes. This threshold value we are talking about. Shriram? Yes, you can look at the formula for FPR. I don't want to go into that, Shriram. Just understand the concept, okay? You check the formula for FPR. Okay, great. So let's move forward. Another algorithm that I want to talk about, it's an unsupervised technique. I will not spend that much time. I think it's pretty easy to understand. In clustering, we create clusters which are very much similar within and very different from the other clusters. And k-means clustering is the algorithm is the most popular one used for clustering purpose. It is a centroid based algorithm, or you can say that it's a distance based algorithm. The points which are close to each other will be put in one cluster, which are different, which are farther away will be put in different clusters. Okay. where we calculate the distances to assign a point to a cluster. In k-means, each cluster is associated with the centroid. The main objective of the k-means algorithm is to minimize the sum of distances between the points and their respective cluster centroid. And these are the steps here. We start with how many clusters we want, which is a very challenging question sometimes, that we have no idea how many clusters this data set can have. But somehow we have to start with somewhere. So with some gut feel, with some knowledge, we pick out what is the number of clusters. There are various techniques also which can help us to guess it. Okay, so let's say here we want to create 2 clusters. So we pick 2 random points from the data and centroid. These points can be any point. Let's say we pick this and this. Then we assign all the points to the closest cluster centroid. So we find the distance of this point from this centroid, from this centroid. Wherever it is minimum, I assign it that cluster. So I make it red. Okay. So all this get reds and all this get green because they are closest to them. Then we recompute the centroid. So now this will become my cluster. These are the points. So what I'll do, I will take the average of these points and recalculate the centroid. This comes at there. It is not aligned to any data point. It has just been created like this because we have created the average of all the data points. Now we will recalculate. We repeat steps 3 and 4. We find the distance of this from here, which one is the minimum. I assign it that cluster. So this is what happened. And we keep repeating it till, what is the stopping criteria? Centroids of newly formed clusters do not change and points remain in the same cluster. They do not move among clusters, and maximum number of iterations are reached. Sometimes we don't want to wait for the first 2 points because it will take a lot of time. So we assign that go maximum 50 iterations to reach the best clusters. Okay, so this was about k-means clustering. Mithun, because means is similar to centroid. How do we calculate centroid? We take an average of all the points, right? We take a mean of all the points. So let's say this point is, I don't know, 2, 2. This is 2, 1. This is, I don't know, I'm just making up numbers, people. 3, 5, 4, 6, and this is 7, 8. So how do we calculate this centroid? We will do 3 plus 2 plus 4 plus 2 plus 7 divide by 5. Similarly, 5 plus 2 plus 6 plus 1 plus 8 divide by 5. Because we are taking a mean to find out centroids. That's why it's called k-means clustering. K is the number of clusters. So you can say it here, it is a 2 means clustering. If you pick 10 clusters, it will be said 10 means clustering. K is the number of clusters. Okay, great. Okay. Now, besides this, I want you to revise and remember these few of the important points. I don't have time to go through these, but you can check the async material for the same. Okay, so some of the important things. So you should know about steps of clustering algorithm. There are 2 major steps, as I have already explained. Assignment, where you assign the points to closer to the centroids, and then optimization. Optimization is when we recompute cluster means and when we assign them to the closest cluster. Then you should know about Hopkins score. It can be created using some Python code, but the interpretation part is more important. Hopkins score we use to check cluster tendency. Okay, so what does it mean? That if my data is having some visible clusters or not. Some data set are like that no clusters are possible there. So this score gives us some visibility that this data is suitable for clustering or not. Let's say if I get Hopkins score as 0.3, it means that data is not good for clustering. And anything more than 0.7, data is good for clustering. Okay, then there is silhouette score. You should be familiar about that. You should be familiar about its formula and its meaning also. Okay, it helps you to find out how good cluster, what is the quality of the cluster. So it gives you that how much it measures the homogeneity of clusters within and the heterogeneity of clusters of heterogeneity among clusters. Okay, so we want those clusters which are very similar within and very different from the other. So this score gives us this information. And then finally the dendrograms, which is part of hierarchical clustering. So here hierarchical clustering creates something like this. These type of dendrograms. So wherever we cut, depending upon that, it creates clusters. So here you should be able to interpret the dendrograms also. It will create 4 clusters here. Okay, so these are some of the things that you should be aware about in clustering. Okay, so these are some of the questions. You can look at these later. These are the explanation has also been given. I want to move to the Python coding question. I want to show you a couple more there also. Okay, I'll take a pause here. Any question I'll answer. Otherwise, I'll move to the Python questions. Okay, again, people, you're gonna be tested on intermediate Python questions of difficulty level as intermediate. Okay. Mithli is asking, how can we find that our choice of k value is wrong? So Mithli, if you get bad Hopkins score, bad silhouette score, it is an indication that you have not picked the right k value. That's why you should do clustering using, I think, range of clusters. To pick a range of numbers. So start from 2, 3, 4, 5, 6, 7, 8, run your model, get the Hopkins score and silhouette score for different values of k and pick up the best one. You look at the async material, an example has been given there, how to do that. Yes, elbow curve will also give you the similar information. Wherever there is an elbow, at that place, the silhouette score is, I think, the maximum, or the Hopkins score is maximum. That will be the ideal value for K. Okay, so no more question. Let's move to the Python sample question. Okay, so again, I will just give you a few examples. Similar questions can come. So let's say question can come to make some type of pattern. Okay, so let's say you'll get something like this. You 0, 0, 0, 0. They can ask you to create this type of pattern. Okay, so how do you create it, people? What thing comes to mind if you have to create a pattern similar to this? What do you think? How can you achieve this? Yes, you can either use np.zeros, that thing, or you can use the nested for loops. Okay, let me try it with nested for loop. You can try it with np array also. And what is the logic behind it? Let's build the logic. So we can say so let's look at how many columns are involved. 4 columns are involved and 4 rows. So for I in range 4, for j in range 4. Okay, so how will we build the logic? If I is equal to 1 or I is equal to 2, these are my rows, and j is equal to 1 or j is equal to 2. Okay, so I'm talking about this pattern here. If I is equal to 1 or I is equal to 2 and j is equal to 1 or j is equal to 2, print 1. Else print 0. This is the logic that you have to keep in mind to create patterns like this. Another pattern can be, people, that is a homework. You can try it. So let's say they want a pattern something like this. Creating an A. So try to build this pattern using nested for loop, writing A. Then you again consider how many columns, how many rows are involved, and accordingly you build this pattern. That is a homework. Let's try this one in the Jupyter notebook. Okay, that will give you some idea how you can solve this. People, please say yes in the chat window if you are able to see my Jupyter notebook. Okay, so let's build this thing for I in range 4, for j in range 4. If I is equal to 1 or I is equal to 2, and let me see if you're able to see. Okay, and j is equal to 1 or j is equal to 2, print 1, but don't go to the next line. So that's why I'm saying end is equal to nothing. Okay, else print 0 and end is equal to nothing. And then print here. Oops. Okay, but this is how you print it, but most of the time they want this pattern. They want you to return this pattern in form of nested lists. Okay, so make sure that if they want you to return this pattern, you return it through a list. So I'm defining a new list. Okay, then I'm saying for I in range 4, I am defining another list, empty list. And then instead of printing, what I'm doing, I am doing b dot append 1. And here I am doing b dot append 0. And here I am doing a dot append b. And then I am returning a. Okay, so this is one example. Another example, I want to give it find out the nth largest number in a list. Okay, so a list has been given. Let's say this is my list. Okay, I want to find out the nth largest number in this list. And let's say that number is, the nth number I want is 3. The third largest number in the list. How do we do it? We'll do step by step. First, I want to get rid of all the duplicate values. Okay, the best way to do that is, the easiest way to do that is convert this list to a set. So I'm converting this to a set. All the duplicates are gone. Then I'm putting it back to list. Oops. And then I am sorting it in reverse order, in descending order. Okay, and then I want to find the third item. Third number is 6. Okay, so how can I find out what is its index? 0th, first, second index. To get the second index, I will do n minus 1. Okay, so you can do something like this. Okay, and last question, let's say the requirement is find number of times a substring appear in a string. Okay, find number of times a substring appears in a string. Okay, let's give you an example. Let's say there is a string called like this. Okay, so how many times the substring AB is appearing in this string? What do you think, people? How can you figure it out? Any idea? Convert to list. Yes, that can be one option. But again, when you do that, again, you have to build a very lengthy logic that you concatenate two elements, check those. Okay. So again, that can be done, but there is a better way which I can think about. You know the method called starts with. Okay. So let's say S dot starts with substring. So what will it return? It will return true. So it is starting from the very beginning. Can I do that? Can I say check whether the S1 starts from 1, go till the end and check whether this starts with SS? So this doesn't start with SS. Similarly, can we check 2, it starts with SS? Yes. 3, does it start with SS? No. So using this logic, we can build a for loop, right? So for I in range, so how we want to go till the end of we want to do iteration as the length of the string. Okay, let me build a counter. Counter is 0. So anytime this returns true if S starting from I starts with SS. If it returns true, increase the counter. And finally, give me the counter. So it will run for 0th index. So starts with 0, then with 1, then with 2, then with 3, go till the length of it, and then count those many times. So AB is repeating 5 times here. Okay, so people, with that, I come to the end of this session. We have covered a lot of ground, and I'm hoping that I have cleared many of your doubts and made you better prepared for the exam. I'm still here for next 5-10 minutes. Okay. In the meantime, I'm going to share this Python Jupyter notebook right away. But before that, I'll still take your question, people, so don't leave yet. Let me launch, the feedback form first. Okay, so people, please spare a couple of minutes filling up this feedback form. It is very important for us, and I'm hoping that you have liked this session. I have tried my best to keep it as simple as possible and still giving you all the tips and tricks, and also explaining you the complex concepts also, especially p-value, adjusted R-square, and so on. Again, some of the concepts are heavy. I want you to probably go through this web recording one more time to clear your doubts and queries. All the resources will be shared with you shortly, along with the web recording and the PPT with my handwritten notes. Okay, again, the practice is the key. Not only practice the questions that I have given, practice all the async material MCQs also, and all the other concepts of ML1 modules also. Go through the async material, go through this web recording again. The more you practice, the better you will become in this. Okay, let me share with you this notebook right away. Okay, please finish your feedback form. I'll give you some more time, and then I will share with you the link of the Jupyter notebook, and as well as take the queries if you have any. Ten more seconds, people, then I will stop publishing the feedback. Please submit it if you have already not done that. Okay, let me finish this thing and let me see if there are any questions. I'm also Sam, you can send me a LinkedIn request, and I will can connect with you there. Okay. Everybody, please let me know if you were able to download the PPT, download the Jupyter notebook successfully. Thank you so much for your lovely comments. If you like the session, it makes me very, very happy. Okay, hold on a second. Just give me a second, people. I am giving you the link of this Jupyter notebook. Okay. I don't know why I'm getting this. Okay, so everybody please check if you're able to download. I think you should be able to. Okay, great. Okay, so with that, people, we come to the end of the session. Thank you so much for your time and patience. I know 3-hour sessions are really difficult. I wish you all the very best, not only for this exam, for all the exams in your life, for all the projects, all the further assignments, for your career and for your life. Probably I'll see you in and some more live sessions later. Till then, goodbye. Take care. Stay safe. Thanks, everyone. The PPT will be shared with you along